All right, hello everybody. We're back, and today we're going to talk about hypothesis testing. And I'll just pause here at the beginning of this lecture and say that this is kind of a concept that's really at the core of what most social scientists do with statistics. So I want to walk through it slowly and in detail to make sure you understand it. In fact, I'm going to split this whole lecture up into three parts, I think. So we'll just cover kind of the basics of the procedure for this first part, and then we'll get into sort of the implications in part two. But stay tuned, I guess, because there's a lot more coming and it's important. So make sure it all is clear before you're done watching this lecture. So how do we get into this? Well, where were we? Last time we talked at length about how to calculate a confidence interval for a particular data sample. And we're going to use some of the same concepts, or we're going to apply some of the same concepts we use for confidence intervals, but in a different way when we do hypothesis testing. So normally when we generate confidence intervals, we want to make a guess about the parameters of some population of interest. So, and normally we talk about this with respect to the mean. The mean is the parameter you'd be interested in, whatever you happen to be working on. So we actually don't do that sort of thing all that often in linguistics. I may have mentioned this before, but we don't usually care about, say, a specific like VOT value. Sometimes we might, sometimes we don't. In other domains, I've learned that other people actually do care about specific parameters of interest in populations that people might be studying. So for instance, my wife does marketing research, having moved on from her linguistics career. So in marketing research, people really do want to know, say, like how many people will buy a new product if they're trying to produce it. Or I can give you another example. Seems like every single time I teach this class, there's a Canadian election about to happen. So there's a Canadian election about to happen right now, and you can repeat this video as many times as you want. I guess it'll be true in the future too. But in elections, pollsters want to really know how many people are going to vote for this party or this candidate or whatever, right? And you can take a look. There's a couple of nice websites out there about the Canadian election. There's one here called 338canada.com. There's also one run by the CBC. This, I guess, is the more private interest one. And this is the, we all pay into the coffer to make the CBC happen. But they both have estimates about what percentage of the vote the various parties are going to get, right? And this one's a little more statistically rigorous, but this is basically an estimate of what the percentage of people who will vote for the conservatives or liberals or what have you. It's a confidence interval, though, around it, though. So, like, for the conservatives, they're giving 33.7% plus minus 4.5%. It's the confidence interval is the same for the liberals, so on and so forth. But the estimate of the mean is a little bit lower. They don't do that sort of, they don't give you the intervals here for the percentage of the vote on the CBC website, but they do give you that for the estimate of how many seats each party can win here. And there's something about that here too. Down here. So, I mean, they're a little bit different, right? So they're going to use different data sources, but generally speaking, they're in the neighborhood of each other, which is, I guess, kind of reassuring. That's where that comes from. And you notice the confidence intervals are different, but they're plus minus some mean, right? We don't do that in linguistics all that often, right? It's possible to think of scenarios where we might want to, say, get a specific estimate of the average F0 for male and female speakers in a population. Or like I said, the specific estimate of like VOT is one I can think of as well from phonetics. I talk about these like estimates of average F0 for males and females when I teach phonetics, just to give people a sense of like, how often your vocal folds are opening and closing when you speak. And that depends on, your biological sex and whether you're an adult or a child, that sort of thing. Normally, however, instead of estimating a mean, we'll test whether there are meaningful or significant differences between two groups of speakers or conditions when analyzing our data. And you'll hear this term quite a bit in when people present their statistical results in an academic talk. That term is significant. And what we're going to learn today, or start to learn today, is what that means when people say it's significant or not. But the main point, though, is that we use this sort of method called hypothesis testing, normally in linguistics, to look at differences between different groups, two or more groups of speakers or conditions or what have you. We don't worry quite as much about what specific mean values those groups or conditions might exhibit, but that's okay. But in order to do this, we're going to use a technique called hypothesis testing. And, I don't want to get too intellectually pompous here, I guess, but you can kind of go back to sort of like the Saussurian school of linguistics and say that, it's not sort of the specifics that actually matter when you're looking at, linguistic categories, but like the difference between them, right? The post-structuralists are all getting upset at me right now or something like that. But yeah, so there's significant differences that we get in language. How do we kind of verify that using statistics? Well, we're going to bridge our way into the technique by first testing whether the mean of a population has a particular value. Kind of sort of like what we were doing with confidence intervals by focusing on a particular value, but then looking at it sort of upside down to what we did before. So what we're going to do is effectively generate a z-score for a sample mean with respect to some hypothesized population mean. And we also have to take into consideration the standard error, which is the standard deviation of the sampling distribution. So I've got this word effectively in here, and down here I'm putting z-score in quotes because what we're going to wind up doing is not actually calculating a z-score, technically speaking per se, but it's going to be very similar to a z-score. And once we have that z-score, we can convert it into a probability based on where it puts us on the sampling distribution. And then that will give us a sense of how likely that sample mean could fall on that sampling distribution. All right, so just to walk you through this process again, because it's not easy to understand, we've got a hypothesized population mean, then we collect a sample mean and calculate a standard error. On the basis of those sample statistics, we are able to calculate a z-score, and then we can convert that z-score into a probability. And then lastly, we're going to get a sense based on that probability whether or not this hypothesis is reasonably valid for the data we've collected. Okay, that's why I put the word at the top of this slide, because like, wow, what's going on? There's a lot to think about here. And I guess before I walk through it again, I'll reiterate that when we do statistics, ultimately we're making an educated guess based on our data. We're making hopefully the most reasonable educated guess we can based on what we've observed, to try to make inferences about what we can't see, all the data that we can't collect just because it's impractical to do so. Okay, so with that in mind, got to take a little bit of a leap of faith here. But what we're doing is we're making this hypothesis about the population mean, and that hypothesized population mean is just going to be whatever we say we think it is. So we're going to just guess, well, maybe the population mean is this. And then we're going to work from there, right? So you can base this hypothesis on, perhaps previous studies of the same topic or just a reasonable guess again, right? Somewhere in the neighborhood of where you might expect it to be. And this is going to be different from our confidence interval strategy. Like I said, we're kind of turn that upside down or on its head a bit. In a confidence interval, when we calculate one of those, we use a sample mean as a reference point to guess where the population mean might be. So we're going from something we've observed to a guess about something we can't totally observe, right? The population mean. Here, we're going to use a hypothesized mean. We're going to say, well, we're not going to observe all the data we need to get to figure out what the population mean is, but we'll guess it's here. We'll say it's 100, whatever it happens to be, right? And then based on that hypothesis, we use that as a reference point to determine how likely it is that the data we do collect could have come from a population with that mean. Yeah, so I'll walk you through the process, and one of the things we have to do on top of that is use the standard error as a way to determine the distance between the two, the sample mean and the hypothesized mean. But we're just putting the hypothesized mean out there, like, oh, it might be 100. And then we get some actual data, and then we see how it compares. And the further away those two are from each other, like the less likely the sample mean is to have come from a population with that hypothesized mean. That's the basic idea. Give me a second. And then we'll give this a whirl. Okay, so let's start by heading back to the set of VOT data that I collected for this class the first time I taught it back in 2011, which somehow is 10 years ago. I think we've been through that, but old age never becomes familiar. It's like, wow, what's happening to my life? Well, I'm collecting data in my life and I'm trying to explain it. So we've got VOT data here in a data frame, and we're going to test the hypothesis that the average VOT for the aspirated stops in this data set is less than 100 milliseconds. So just to review, this is what the VOT data looks like. It's similar to what we just did in the first homework exercise for this class, except the first time I taught this class, I didn't really know what I was doing. I had people produce both aspirated stops and unaspirated stops in English. So we've got both positive and negative VOT values here over on the right-hand side. I want to focus on just the aspirated stops in this data set. And our hypothesis is going to be that the population mean of those aspirated stops is 100 milliseconds. And I want to test the possibility that the actual observed sample mean of aspirated stops is going to be less than 100 milliseconds. So we're just going to put that hypothesis out there. It's 100. What I observe something close enough to that I can say, well, maybe that's probably what the actual population mean is. So we'll do that by subsetting out our aspirated stops. This is nothing new, hopefully, now that we know how to play around with R a bit. We're going to pop those over into a vector called aspirated. And then I am going to, actually, I don't think this is a vector. I think it's another data frame. But anyways, I'm going to run the test the way you would normally run it. And like I said, we don't actually look at Z-scores when we're doing this. We look at something called T-scores, which are quite similar. And for that reason, what we're going to run is a test called a T-test. And the way you run it is with this command. It's t.test. And then you have a variety of different parameters that have to go within the parentheses here. And hopefully this should make a fair amount of sense based on what I've just been talking about. But aspirated $VOT, I'm just going to look at the VOT values for the aspirated stops in this data frame. This mu equals 100. Mu, remember, is the way we represent our population mean, the Greek letter mu. That we're hypothesizing is 100 milliseconds. And we're going to test this hypothesis that our actual sample mean is less than that. And all I got to do here is put this in the right order within the parentheses and then hit return, and it's going to give me an answer. We don't know how to interpret it yet because it's just going to look like a lot of numbers, but that's what it's going to tell us. So it says one sample t-test. It's got all this information. It's got a t-score. This is degrees of freedom. It's got a p-value, so on and so forth. At the bottom here, though, it's got something which we do understand by now, which is the mean of the x, the mean of the data that we're actually testing. So we hypothesize that it's 100, and we find out that the actual sample mean is 94.18571, what have you. Interestingly enough, we don't look at this a whole lot when we actually start running these tests, but it gives a confidence interval. This command does in R. And this confidence interval, not too tight, I guess you could say. So at the upper end, it's guessing that the actual mean is 97.5. And at the lower end, it's guessing that it's negative infinity. So somewhere in there, we get the actual population mean. But the fact that the upper end is 97.5, and that does not include 100, kind of gives you a sense about where this might be going. But that's all I'm going to say about that for now. Let's get back into it, and I'll show you kind of the nitty-gritty details of where those numbers come from. So I'm going to double-check the math by running a z-test for the same hypothesis, which should hopefully be a little more understandable based on what we know at this point in time. So we can find out what the mean for our aspirated stops is another way, right? So we can just use this mean command. And lo and behold, it actually looks the exact same as the mean of the sample that was spat out at us by the t-test command. So that's reassuring. We can also look at what the standard deviation of the sample is. And I'll pop that in here. And we get a number, 29.2. Okay, well, what does that mean? It's hard to say, just that's the amount of variation that we're getting in these VOT values. And I'll just remind you that we're dealing with sample statistics here down at this part of the slide. But what we really care about is the standard error of the sampling distribution, right? So we can only get so much out of the sample by itself. We want to find out how that sample fits on the sampling distribution for the entire population. And remember, we're hypothesizing the population mean is 100. But if we take multiple samples from that population, we'll wind up getting means that sort of form or should form a normal distribution centered around that mean of 100 milliseconds. Okay, so for that, the standard deviation of that sampling distribution is going to be called the standard error, and we can estimate that by dividing the sample standard deviation by the square root of the number of items in the sample. We've seen that on previous lectures. Here's what it looks like when you actually calculate it. So we're just going to divide what we just saw up here, this 29.2, by the number of observations we have in the aspirated data set. It turns out there's 210. There's 420 data points overall in this data set. Half of them are unaspirated, half of them are aspirated. So we're dividing by the square root of 210. I'll let you do the math about what that actually is. Off the top of my head, what is it? Something like 14 something, right? So when you divide 29 divided by 14 something, you get 2 something. So a little over 2 is going to be our standard error for this particular data set. Okay, and so what do we do with that? We can now calculate a z-score for a hypothesized mean VOT value of 100 using the standard error rather than the original standard deviation, because again, we care about sort of that population standard deviation rather than the sample standard deviation. And sorry, not the population standard deviation, I meant the sampling distribution standard deviation, which is called the standard error. Okay, and so for this, we just go back to our old formula for calculating the z-score, which is that you take your observation and you subtract the hypothesized mean from it, and you divide that by the relevant standard deviation. And in this case, we're going to get a z-score of negative 2.88. So remember that our observed mean is less than 100. So our observed mean is about 94. Our hypothesized mean is 100. So 94 minus 100 is about 6. Or about 94 minus 100 is about 6. And then divide that by about 2. You should get negative 6 divided by 2, which is about 3. It winds up being not quite that. It's negative 2.88 when you let R do the math for you, but hopefully you can see where that's coming from. Okay, so now we have a z-score of negative 2.88. If you jog your memory, go back to what we talked about with respect to z-scores, perhaps you can recall that that's relatively far to the left or beneath the mean of the distribution that we're talking about. But kind of more importantly, or at least more relevantly for this slide, if we go back here to the output of our Ttest command, we see that t equals negative 2.884, which is basically what we're getting here for the z-score. They're effectively the same value, even though they're calculated slightly different ways. Yeah, and then again, we said when we first looked at this that we didn't really know where this is coming from. But what I want to relate now is the connection between the t scored here and the p-value there. So if I just take calculate the p-value for that z-score, I'll get something which looks very similar to the p-value I got for the t-test. So this is 0.00196 something, and this is 0.002. Both of these values are around 0.002, which is a relatively small number. And so remember, basically what we're talking about when we're converting z-scores into probabilities is we're looking at sort of like what's the proportion of the normal distribution that falls to the left of that z-score. And this z-score is so small at negative 2.88 that not a lot of the distribution is to the left of it. It's about 0.2% of that distribution. Okay, give me another second. I want to talk about what that number means, that 0.2% means, but I'll point out first that we could have skipped all the steps we just ran through above and just run the entire z-test at once with the following command, which is to put everything in parentheses that's relevant for calculating the z-score, because what we want to get out of it, or kind of the main interpretive device we get out of it, is that p-value. So if I just put all of what I need to know to calculate the z-score in here, and then just hit return, I'm going to get the same answer, about 0.2% or 0.2% of the or the proportion of the distribution is about 0.002. Yeah, you can do it the easy way that way, but really the easy way to do it is just to run the t-test like this. But just so you know where all these numbers are coming from, that's where they come from. And on top of that, I'm going to point out that what we've observed already, the p-values for the t-test and the z-test differ slightly. And that's because the t-distribution used to calculate the p-value for the t-test is not quite normal. It looks like a normal distribution, but it's shaped slightly differently. And the extent to which it's shaped differs from the normal distribution depends on how many data points there are in the sample you're testing. So that being said, I'm going to try to cover that in the third part of this lecture after part number 2, which is how do we interpret this. So stay tuned for that, but I don't want to dwell on it for now. For the moment, I kind of want to give you another view of how this works. So in case any or all of the above didn't make any sense, we can think about the nature of a z-test in graphical form too. So we'll take a look at our estimated sampling distribution if that sampling distribution has a hypothesized mean of 100 and a standard error of about 2. So again, we're just positing that the mean is 100. And this standard error measure comes from what we observed in our sample, right? Remember, that's that 29 divided by, the square root of 209 sort of number. And it will look like this. So the mean of this normal distribution, which the sampling distribution should be normal if our n is large enough. And it is centered around 100, and most of it kind of falls within 95 to 105. And remember that the mean we got for our sample was at 94. So it's low down here on this left tail of the sampling distribution. So the main point to think about here is that it's pretty far away in terms of like the shape of this distribution from the mean, and there's not a whole lot left over here on the left-hand side that's lower than that sample mean. So that gives us a z-score of about -3. It was -2.88, whatever. And so there's only about 0.2% of the distribution to the left of that value. Okay, so maybe if you can see it, it makes a little more sense. Normally, I write this up on the board as we're walking through the process and kind of have to do it in 2 different ways here using PowerPoint and a video, but maybe after talking about it multiple times, it makes more sense. The real important question, though, is if the underlying population mean for our VOT data is actually 100, then we'd get this observed sample mean about 0.2% of the time. That's not very often, right? Expecting something to happen 0.2% of the time is not going to happen very often at all. So I think that's like 1 out of 500 times. So how should we interpret the results of this test? Basically, we need to be able to answer the question, should we accept or reject our hypothesized mean? We're positing the mean of this population is 100. Now we have some data that reflects upon that hypothesis. Knowing what we know now from the results of our little experiment, should we keep believing that the mean of the population is 100 milliseconds or not? Should we accept that hypothesis or should we reject it? And I'm going to actually pause the video here because it's the end of part 1. But in this particular case, I want to ask you, what do your instincts tell you? Should we accept this mean or should we reject it? I want you to stay in tune with your instincts throughout this class because they're important. Nothing's going to make sense unless they make sense to your instincts. So give me your instinctual response to that question, and I'll answer it at the beginning of part 2.